my lab in particular is interested in understanding how these physical forces and changes in protein structure affect wound repair processes, so driving more regenerative wound repair versus fibrosis, or how pathologically you would have processes that would drive metastasis, like changes in the tumor stroma, creating tracts that would allow a tumor cell to migrate to a distant organ.
Welcome to Owl Speak, where we discuss what's going on at the Temple College of Engineering. I'm Casey Tinney, your stand-in host for today, who will let you in behind the scenes with our Temple engineering faculty and students. Our owls fly high, so I'll keep you up to date on their most interesting innovations. Today, I'm here with Dr. Karin Wang, an assistant bioengineering professor who specializes in cell and matrix mechanobiology. Dr. Wang, we're so happy to have you. How are you doing?
Good. How are you?
I'm doing all right. So let's jump right into it. You run the Cell and Matrix Mechanobiology Lab. So tell us kind of about your research and what's going on in there.
Okay. So what we're interested is understanding how physical forces change how these fibrillar networks around cells control their behavior. So how physical forces change molecular conformation of proteins and how that in turn changes how cells adhere, how cells decide to migrate. And all of these are important in physiological processes like development, wound repair, fibrosis, cancer metastasis, or any other sort of fibrotic diseases. My lab in particular is interested in understanding how these physical forces and changes in protein structure affect wound repair processes, so driving more regenerative wound repair versus fibrosis, or how pathologically you would have processes that would drive metastasis, like changes in the tumor stroma, creating tracts that would allow a tumor cell to migrate to a distant organ. So that's the premise of why we're creating these in vitro models. We can do a lot of visualization of these processes on our little dishes in the lab.
Okay, so you do everything kind of in vitro, like you said, and then apply that to... So you're not using any human models, no human...
No.
Got it.
I mean, we use human cell lines that recapitulate dermal tissue or breast cancer tissue. But yes, everything's done with cell lines and not with any sort of like mouse model or whatnot.
Okay, understood. So that's a very... I don't know if niche is the correct word, but specified focus on.
Yes.
So what kind of led you to this focus in bioengineering?
Oh, that's a loaded question. So I started off doing undergraduate research in a polymer science lab. So I was electrospinning these polymer fibers into nanofibrous mats. So using these for tissue engineering purposes, like creating these nanotubes, and we would suture them into blood vessels and make sure that these scaffolds that we're creating allow cells to infiltrate and to repair a vessel. So that actually got me really interested in what was actually happening, because I was using synthetic polymers to create tracks for cells to migrate over and to repair a blood vessel wall, but I didn't understand how that was happening. So after thinking about whether I should go into industry or continue to grad school to do more research, I ended up deciding to do research, and I applied to grad school. That's where I went to Cornell, where I started learning more about protein structure and cancer metastasis. So that was where I started using a little bit more biophysics, biomaterial science to understand how changes in protein structure really affect how cells are able to adhere. And then decided that, I really liked this type of research, wanted to learn more, and kept going on into getting a postdoctoral fellowship where I started learning about how cells collectively migrated together and how that drove different processes, such as closing a wound. You have to have cells to migrate together to close a wound, or migrate together to migrate out of a tumor to metastasize. So all of that came full circle when I decided to start my own lab here at Temple, where I wanted to combine everything. how do these outside-in signals drive cellular processes such as collective cellular migration. So that's what we're working on now, but more in the field of wound repair.
Okay, so you always started with wound repair, like even in undergrad, it was kind of the blood vessels, or?
Yes. Well, in undergrad, I actually did a variety of projects. So I was working also with gels for pain management, controlling, lidocaine release. This was just one of the projects that I worked on. I was also working on anti-hernia patches too. It was all kind of broadly subsumed under the tissue engineering field for a variety of applications. But yeah, I would say that was my first foray into wound repair, and then grad school was more cancer metastasis as well as in postdoc. Then I came back to the wound repair world.
Okay, very interesting. So you mentioned a lot of different research opportunities you did in undergrad. What other kind of opportunities would you say you got in your undergraduate career that kind of led you down the path that you took?
Okay, so when I was an undergrad, I went to a state school because I couldn't pay for, a private school, and I received a lot of scholarships that made undergraduate career pretty much almost free. So I was very fortunate in that aspect that I went into engineering and graduated with little to no debt, basically just an extra year for my +1 master's program. But the opportunities I received at my public institutions, much like Temple here, were, opportunities to do research starting from my freshman year. Opportunities to be part of a Women in Science and Engineering program where, as a freshman, we get mentored how to manage our time, how to even study or prepare for exams. And then that came full circle because then I also continued on into that program and became a mentor for incoming freshmen. So I really like these programs where, you kind of start in as a freshman and then you continue on and then you give back to that same program as a mentor. So I was a part of that program for 2 years as a mentor, where I also helped incoming freshmen, manage their time, help them out through their bioengineering careers and whatnot. Actually, not all of them were bioengineers. We were all a variety of engineers. So there are a lot of really good programs such as that. I'm kind of blanking now on a few others, but also, doing senior design with a dermatologist was really great. Working with, hydrogels and whatnot with these professors. It was really good getting all the hands-on experiences that led me to continue on into the research field.
Yeah, definitely hands-on experience, I've heard from a lot of people, is what, makes them more interested in their career. You mentioned a lot of mentorship opportunities, and in previous conversations you and I have had, you mentioned that you try to incorporate a lot of mentorship in your lab now. Can you kind of talk about some of the mentorship you've taken over in your professional career?
Yeah, so I really do think that students have a lot of opportunities to showcase their independence and how well they can perform if they're given that opportunity. So it kind of drives my own mentorship style. I try not to be too hands-on, because if I'm hands-on, students are not going to learn and are not going to have the opportunity to make their own mistakes. So in my own lab, undergraduate students pretty much run their own projects too. Wow. Yeah. I typically don't like to say, on this day, you're doing this, you're making this solution or whatnot. I give them a little bit more freedom to think through the problem and to drive through how to execute it from what they should be doing to actually getting the result. If they don't learn from their mistakes in a safe environment like my lab, they're never going to be able to do it in the real world. Like, I think a lot of students get a lot of anxiety. If I'm going to fail, I can't do it. So they don't want to do anything. And so that's kind of the premise of how the students in my lab, just go ahead, do it. Talk through it with me if you have any questions. We have weekly meetings. We go through problems that come up, and we try to address it. But yeah, overall, the students in my lab, I try to let them drive their research direction too. Like if they want to try something new based on the literature that they've been reading, that's totally fine too, as long as they give me a rationale for it. It always has to have a rationale. But if they do, that's totally fine.
Okay, that's awesome. And then are there any senior design projects that you're running now? Or
I do have a senior design team, and they are creating a microscope compatible incubator chamber. So a lot of the work we do is on the microscope. We monitor how cells move, how they create and synthesize their own network upon which they can migrate. And we also have a strain device actually created by another senior design team that strains the surface upon which cells migrate over. So part of that process requires us to allow the cells to do their normal processes, but it has to be in a controlled temperature environment, controlled humidity. They have to have access to CO2. And so this is what the current senior design team is doing, creating a chamber that allows CO2 to come in, allows humidity to be controlled and temperature to be controlled. And they have to make sure that it fits over our microscope and our strain device as it's moving to different positions. So there's quite a bit of constraint involved. And so they have a pretty hard project for one semester too.
Yeah, that sounds difficult. All right, so what projects are you currently working on?
So one of the projects that we're interested in is how protein isoform structure also changes cellular behavior. One of the students in my lab, she's interested in how one isoform structure of fibronectin changes the mechanosensitivity of cells during migration, during mechanotransduction while they're migrating. And we actually have a paper in revision right now trying to understand this process of matrix assembly, wound closure, and whether it's driven by this change in isoform structure. Another project that we are also working on, one of the newest graduate students in the lab, is looking at cell-derived matrices and how different phosphorylation, post-translational phosphorylation changes how cancer cells migrate and metastasize. So that's in the very early phases, but one of the students is interested in the cancer metastasis world. So we're getting back into that too.
Okay.
Yeah.
That's awesome. So there's been a lot of, I guess, technical terms. How does all this research you're doing in the lab on the cellular level, what kind of impact does that have, on real people, in the field?
If we're talking about the wound repair space, when you have an open gaping wound, you need cells to be able to infiltrate that tissue so that they can create more tissue and close that wound up to what it was before. One major problem is being able to control this process so that you don't get too much scar tissue. So a lot of times you get too much scar tissue, you sometimes lose functionality, or you get wounds that don't close at all. So some of the work that we're doing is directly applicable to how to make sure wounds actually do close, but also control that closure process so that you don't lose tissue functionality and have excess scar tissue forming. In the cancer space, what we're really interested in recapitulating is the stromal tissue surrounding a tumor, because it's actually the stromal tissue surrounding the tumor that allows the tumor to grow, spread, and migrate outward and metastasize. So if you can prevent this tumor stroma from developing further, you can kind of trap the tumor in place and prevent it from metastasizing further. So a lot of it does have direct applications to everything in the clinical world, but we're in the very, very early phases of creating these model systems so we can actually probe, changes in protein structure and cell adhesion and whatnot, because you can't do that very well in vivo or in humans.
Okay, very interesting. So I guess, you kind of started this topic when you were an undergraduate, obviously slightly different, led you down a different path, but what kind of kept you in the field? Was it the real world impact, or kind of what kept you down this path within, this research?
Definitely the real world impact. Also being able to expose students to the research that we're doing. So it kind of comes full circle. As a student, I had no idea what research was, but it was only because of a class that I was in that I understood that what I was learning in class could be applied and I could actually have a hand in that. So this is what I like to do too. The research that we're doing, it's all driven by students who are interested in this space and who are interested in making an impact in the wound repair world or the cancer metastasis world. I have many students that want to go to med school or want to work in industry so that they can, make the next therapeutic tool or therapy itself. So, definitely a lot of great applications. And I think I might have lost track of the question.
But is that kind of the real world application kept you in your career in STEM,
yes.
Kind of affirmed your choice?
Yes, definitely. I've seen a lot of people with, I've actually, I've done a lot of shadowing in hospitals before during grad school, undergrad as well. And, it's pretty heart-wrenching seeing people going through these processes. And yes, we're in an engineering school and we're removed, but I'm sure all of us have had someone who's had to stay in a hospital because of some sort of, injury, or they were impacted by cancer or whatnot. So all of these drive the research. We're not doing research just for the sake of doing research. We want to do research so that we can help people surrounding us. So that just keeps us going. Just want to make sure that we can, benefit people in society.
That's awesome. Not doing research in a vacuum, kind of looking at the broader world. I guess in your time in this field, both teaching and doing research, what have you seen change, I guess, kind of in the research field and then also in teaching and mentoring? What's changed over the years?
That is a loaded question. I would say the tools have made, the advances in tools and microscopy have made it a lot easier to visualize some of the things that we want to see. Like how can we recapitulate tissue? We're building better models of different types of tissue, of diseased tissue, and we're better able to recapitulate these processes so we can understand what actually went wrong and how can we actually kind of try to change it in some manner or another so that we can prevent that from happening. So I would say there's been a lot of technological advances, a lot of advances in our knowledge of mechanobiology that allows us to do the research that we do. And with regards to the student, I would say they're a lot more driven to make an impact. A lot of them want to make an impact, which is great. It's just, I also think a lot of them do a lot. Like, there's so many students doing multiple things, and I do worry that in their need to help and to create an impact, they might be stretching themselves a little thin.
Okay.
So there is that. I do worry that some of them want to do so much that it may end up kind of being difficult to actually make an impact if they've only got like a finger or two in multiple pots.
Yeah, that makes sense. And then I guess, is there anything else you want to add about your research that we didn't touch on, or teaching or mentoring or kind of anything in your career that you wanted to add?
No, I mean, I think, I couldn't have gotten to where I am without support from family, first gen. So we had no idea what college was all about. All the scholarships that I got from different foundations, from companies, that helped me get through my undergraduate career, get through my PhD, funding from the federal government to fund my postdoc research. That also helped a lot. Like the opportunities from, different institutions, from my mentors to help me, all the cheerleaders as I went through different stages of my life, that definitely was important. And if you don't have, a network of people that are cheering you on or helping you, giving you these opportunities, you can't get ahead in this world. So that definitely helped a lot.
Definitely, I think, that applies to everyone, having people there to support you. I think that's a good positive note to end on. Thank you, Dr. Karin Wang, for joining